Okay, so what we did yesterday is we gave the definition of a strict monoidal category and introduced this string diagram formalism for working with monoidal categories. And then we discussed symmetry in monoidal categories. So we introduced these crossings together with some axioms that they have to satisfy. And that's what it means for a category, a monoidal category, to be symmetric. And what I want to focus on today is the idea of duality in monoidal categories. Okay, so actually a couple of the pictures I'm going to draw today we saw in Ben's talk yesterday, because one example of duality in monoidal categories, or really in two categories, which is a bit more general, is that of adjoint functors, which we saw in Ben's talk. But I won't really be talking about adjoint functors. I'll be talking about duals in monoidal categories, but we'll see the same sorts of pictures that we saw a little bit in Ben's talks. Okay, so we're going to say we're working in some strict monoidal category, and we want to examine what it means for one object to be dual to another object in this general setup, right? So we've all seen dual vector spaces, dual representations, and we want a formalism for this in the abstract setting of monoidal categories that should specialize to these types of duals that we've seen in other contexts. So let's say we have two objects, which we'll denote as up arrow and down arrow. This is a nice little way of remembering that we've got two objects that should be dual to each other, the opposite orientations on the strings. And so if we wanted to have, say, some map from down arrow tensor up arrow to the unit object in our monoidal category, we want some sort of picture that at the bottom has a down arrow and an up arrow, and then has nothing at the top. Because remember, our convention is that the unit object is just blank space. And the identity morphism of the unit object we just don't draw. So when we draw some sort of left cap like this is a natural picture that could represent a morphism from down tensor up to the unit object, right? And so that's the picture that we'll use for the morphism that will be part of our duality. And in the other direction, if we want a morphism from the unit object to up tensor down, it's natural to draw this type of picture, because this picture has no strands coming in at the bottom, so that means the domain is the unit object. And at the top, it's got up and down. So the codomain is up tensor down. Okay, so that's just some pictures that we'll use to represent morphisms with those domains and codomains. So now we can give the definition of dual. Right, so in the general setup of monoidal categories, we have one-sided duals. There's left duals and right duals, just like for functors, you have left adjoints and right adjoints. So we'll say that down is left dual to up, and that's equivalent to up being right dual to down. If we have these types of morphisms, which we denote by these left caps and cups, and they satisfy these relations that are sometimes called zigzag relations, sometimes called yanking relations, because you're yanking the string tight. Topologically, they're very natural relations. This is just some sort of isotopy invariance. But we see if you haven't seen these things, let me be a little bit sort of explicit. If you split it right here, you see below that red line, you've got the left cup tensor the identity. And then we compose that with the identity tensor the left cap, right? So that's how you should think of that, and the same thing here. So it's really an equality between composites. And these morphisms have a name. They're called the unit and the co-unit of this duality. Okay, so again, you saw these pictures in Ben's talk, but let me give you another example just to make this more concrete. Well, first a piece of terminology. If we have a monoidal category where every object has both a left and a right dual, we say that that category is rigid. Right? That's the word I'll use. A word you sometimes see elsewhere in the literature is autonomous, but I'll call it a rigid category. You can have just a left rigid category where every object just has a left dual, or a right rigid category. But for us, we'll be interested mostly in the case where things have duals on both sides. So that's a rigid category. So let me give you an example of this type of duality just to make it very concrete. So let's take the category of vector spaces over some field K. So in this category, the unit object is the one-dimensional vector space, right? Because if we tensor with the one-dimensional vector space, we get back the vector space we started with up to isomorphism. So what are the maps that are going to correspond to our caps and cups? Well, there are these maps. There's some very natural maps. There's an evaluation map, which goes from V dual to V. So now when I write V dual, this is just the vector space dual, linear maps to the ground field. So we have a natural map that goes from V dual tensor V to the ground field, which is just evaluation, right? We take some element of the dual space and some vector, and we just evaluate and extend by linearity. This map has a corresponding sort of, maybe I'll call it the dual, although that's maybe overusing the word dual, but there's a map sort of going the other direction called co-evaluation, which goes from the ground field to V tensor V dual. And since the domain here is one-dimensional, it suffices just to say where the unit in the field is sent. So the unit is sent to this sum. We take a sum over some basis. We fix some basis in our vector space. And we take a sum over V tensor delta V, as V ranges over that basis, and delta V is the dual basis. And then a little exercise that I put in the notes, you can show that this map is actually independent of the basis. So even though when I define it, I've chosen a basis, the map is independent. There are two ways to see this. You can do the brute force way, which is to change basis and just see that everything cancels and you get the same formula. Or if you identify V tensor V dual with endomorphisms of V in the natural way, then this right-hand side corresponds to the identity map. That's sort of the conceptual way to see why this is independent. Okay, but it is independent, so it doesn't depend on our choice of basis here. Okay, so let's check that this really does show that the dual vector space is dual in the sense that I defined for monoidal categories. Okay, so our up arrow will be V, and our down arrow will be V dual. And so our left cap will be this evaluation map, will be the co-evaluation map. Okay, so let's check our relations. So here I've just rewritten, right here I've rewritten this relation 4.1 that we're going to check, right? So let me scroll back. Really, we want to check these two relations. We'll check the left-hand one because the check of the right-hand one is almost identical. Okay, so we'll just check this left-hand zigzag or Yankeean relation. Okay, so I've written that little blue line here to show how we should split up this zigzag and think of it as a composition of two different morphisms. So you see at the bottom, when we start here, we've got V. And now we want this cup here. But that cup, its domain is really the ground field. So here where we have to use this fact that vector space is not really a strict monoidal category. So we're implicitly using this fact that a vector space is isomorphic to the ground field tensor that vector space. Right? So this is just a subtlety that arises from the fact that vector spaces is not actually a strict monoidal category. We're always implicitly using this type of isomorphism. So that isomorphism sends some vector to just the unit in the field tensor that vector. That's that isomorphism. Right? Okay, so now we want to apply this cup here. So that cup took our unit in the field to this sum of V tensor delta V. Right, that's our cup. So that's, we've applied this map, the cup, and then just the identity on the other factor. I've got extra O times I don't want there. And now we're here and we want to apply this cap. Okay, so we take the identity on V, tensor this cap. And remember, the cap was just evaluation. So we take this dual delta V and evaluate it on W. Over here now. Okay, that lands in V tensor K. And then again, we have to use this implicit isomorphism that V tensor K is isomorphic to V. That isomorphism is just scalar multiplication, right? So that we just lose the tensor power here and we just get this sum. But that sum is just how you write W in the basis BV, right? The delta VWs are just the coefficients when you write this in that basis. So you get exactly back, oh, I wrote V, it should be W. Right, so you get exactly back W. So you see this composition is the identity map. We started with W and we ended with W. Right, so that exactly shows this relation. We show that this zigzag is just the identity map. Okay. And so you can do the other relation, this one, in exactly the same way, or it will follow from something that we're going to show later, that because we've actually got some symmetry in this category of vector spaces, being left dual implies that it's also right dual. But you could also just check this in the exact same way. Okay, any questions on that computation? And even though I worked in vector spaces here, you could be working with modules over a group or modules over a Lie algebra, and it's the exact same proof that shows that the dual that you're used to in the traditional sense is the dual in this categorical sense as well. It's the exact, you use the evaluation map and the co-evaluation map, this exact same proof. Okay, so from now on, our convention is that cups and caps will always denote units and co-units giving a duality, just like we adopted the convention that crossings were this special type of morphism that's involved in symmetry data. And then another exercise that I'll leave for you to read in the notes, but I'll just say in words what it's about, is you might wonder how unique this unit and co-unit data is. That gives a duality. And in general, it's not unique. So for instance, if you pick any non-zero element in your field, you could scale the cup by that element and the cap by the inverse of that element. So they're certainly not unique. But if you fix one, if you fix the cap, you can show that the other one, the cup, is uniquely determined, right? So that's what the exercise is. So we've got this sort of freedom. Okay, so now let's do what we did with symmetric monoidal categories. So after defining a symmetric monoidal category, we defined a category that has a universal property with respect to being symmetric monoidal. So let's do the same thing for duality. So this category turns out to have a nice name. It's called the oriented temporally lead category. It's probably a little bit less well known than the unoriented temporally lead category, but there is an oriented temporally lead category, which is what I'm about to define. So we've got two generating objects, and we want them to be both left and right dual to each other, right? So we now know what that means. We need a left cap and cup for down to be right dual to up. And then we need the cap and cup in the other direction for it to be dual on the other side, right? And then we have these zigzag relations, but now we have both forms of them, ones that involve the right caps and cups and the left caps and cups, because we want it to be dual on both sides, right? So we've taken two objects and we've exactly thrown in the morphisms and relations that we need for these objects to be both left and right dual to each other. Okay, so what does this category look like concretely? So objects in this category, because we just have these two generating objects, up arrow and down arrow, the objects are just finite tensor products of those two objects. So up, tensor down, tensor up, arbitrary tensor products, and the empty tensor product, which is the unit object. And then morphisms are any diagram that we can build with cups and caps oriented to the left or right, and identity morphisms, which are just strands pointing straight up or down. So you can make these types of diagrams, right? You can have these components that are just closed because you can put a cup on top of a cap. Your strands cannot cross each other because in this category, we don't have any crossings. We just have cups and caps. And that's the type of diagrams. And you can take linear combinations of them because we define this to be a linear category. And so the domain, you read off the bottom. So at the bottom here, we've got up, down, down. So that gives us the domain of this morphism. And if you read across the top, we've got up, down. And so that gives us the codomain. Okay, so sometimes you might see this with an extra condition, which is that you impose the condition that these bubbles are equal to some scalar. We'll come a little bit later to the meaning of that, but you don't have to impose that condition. You can have these free-floating bubbles, and that's fine. Okay, so this is the free monoidal k-linear category on one object with a two-sided dual. Okay, so what does that mean? If you have any other k-linear monoidal category, C, and you pick two objects, X and Y, that are both left and right dual to one another, then there's a unique monoidal functor from this oriented temporally lead category to that category that takes up to X and down to Y. And it takes the cups and the caps to the unit and the co-unit of this duality, right? Because when we say that x and y are both left and right dual to each other, we have in mind that we fix this unit and co-unit. So that's where the caps and cups are set. And so that's its universal property. Any questions there? Yeah, you can add in, and in fact, we're going to do that. We're going to make it symmetric monoidal by adding in crossings. That'll be the next step. Yeah. Or if you don't want to make it symmetric monoidal, but braided monoidal, you could add in over and under crossings. Yeah. Any other questions? Yes.
Is unoriented without the error? So
yeah, if you take, and I'll define that one. So the temporally lead category without the word oriented is just your strands are unoriented, but the pictures look identical. In fact, the pictures I'm going to draw, I just copied the sticks and I just removed all the arrows. It's the same thing. Other questions?
I guess it's duality kind of be based on up and down.
Pardon me?
Is there a duality based on up and down?
Yeah, this category has some symmetries, right? You have a symmetry where you reflect in the vertical axis. That takes this category to its opposite category, or it's a contravariant functor. You've also got a symmetry where you flip in a vertical axis, and that takes this category to the reversed category where you reverse the tensor product. Yeah, so there are a bunch of symmetries. Because these objects are left and right dual to each other, so that's a symmetric condition. Other questions? I mean, when I was preparing these lectures, I thought about introducing even before this, you can have a universal category with an object that just has a left dual where you only have left caps and cups. It's just you hardly ever see that category. So I decided just to skip to this one where we have left and right caps and cups. But hopefully you get the idea. You can create all these sort of universal categories. And a little exercise, show that this category is a rigid monoidal category. Remember, that means that every object has a left and right dual. So we've defined it so that these generating objects, up arrow and down arrow, have a left and right dual. You need to show that an arbitrary object, which is a tensor power of these, has a left and right dual. And the hint is, this is a very easy exercise. The hint is you just nest the caps and cups, and that will give you the duality for an arbitrary object.
Sorry.
Yes.
So this morphism, this factor from OTL to C would define an orientation over C. Is it?
Well, the orientation for us is just sort of a bookkeeping to keep track of whether it's this object up arrow or down arrow in the domain or the codomain. But yeah, you could think of that. Now you can draw pictures in C where your X you'll denote by up arrow and Y you'll denote by down arrow. But C may have other objects, so you're sort of not putting an orientation on the entire category, just on the sort of category generated by these two objects. Okay, so we've discussed symmetry and duality, but now where things really get interesting is where you put the two together. We want a category to have both symmetry and duality, and we want to see how those two things play with each other. So now we're going to assume throughout here that C is a rigid, symmetric, monoidal, k-linear category. I should also say strict. Okay, so rigid, remember, means every object has both a left and a right dual, so we have the duality, and now we're also requiring it to have symmetry, be a symmetric monoidal category. And we want to see what type of things follow right from these axioms, right? From the fact that it's both rigid and symmetric monoidal. So remember, part of being symmetric monoidal is that the crossings are natural in the two arguments. So that meant that these morphisms, which we will denote by some sort of token, slide through crossings in both directions. But in fact, a note I wrote here that will be important for us later, it's enough to just impose this equation on the left, because then if on top of this you put crossings, and then you use the fact that this is equal to this, it gives you the one on the right. All right, so in fact, we'll just almost always focus on the one on the left a little bit later. But for now, let's write them both down. Okay, so let's suppose that we've got some object up arrow. And our category is rigid, so that means it has a left and a right dual. So let's say the left dual is down arrow. Okay, so let's take this equation 3.3a here, and let's take the special case where this F is actually the left cap. So the left cap slides through the crossing. So that gives exactly this equation. Now, if you're not used to these things, you might complain a little bit, well, this had some strand that crosses through and there's no strand here. Well, it's because there's a hidden strand, which is the identity morphism of the unit object, which we don't draw. That is sort of getting pulled through there. But the idea is that the left cap pulls through the crossing. That's naturality, right? So we don't have to impose that condition. It follows from the axioms. And similarly, if we take this equation 3.3b, and we take F to be the left cap, then it slides through the crossing. We get that type of relation. Okay, so this just some compatibility we have to have if our category is rigid and symmetric monoidal. Similarly, we can take F to be the left cup, and the left cup slides through the crossing, right? So in both directions, that gives us these two equations. Right? So this has to be true in any rigid symmetric monoidal category, that caps and cups have to slide through crossings. Now, a little exercise, use these two equations, 4.5 and 4.6, to deduce these ones. So these ones usually people describe as saying that crossings slide over caps and cups. And so the hint, if you're not used to these things, you take 4.5 and 4.6 and add some crossings in appropriate places. And then use the fact that in a symmetric monoidal category, you can always pull apart double crossings. And then you can get from 4.5 and 4.6 to these cap and cup slide qualities. Any questions? Okay, so let's keep going. So now let's come to what I think is sort of the first significant proposition, and I want to go through the proof to give people a flavor for how you can prove these types of things using string diagrams. If you have a symmetric monoidal category that has some object down arrow that's a left dual to an object up arrow, then it's also right dual. And what's key here really is that we're working in a symmetric monoidal category. So this is not true in an arbitrary monoidal category. But if we have a symmetric monoidal category, then left duals are automatically also right duals. Okay, and you can give a really nice string diagram proof of this. Okay, so here's the proof. Okay, so first of all, the equations that we have are these ones. These are the ones that say that down arrow is left dual to up arrow. And the ones that we want to prove are these ones, which say that down arrow is right dual to up arrow. So we have to get from this 4.1 to 4.2. So all we have so far are left caps and cups. We need to define right caps and cups and then show that they satisfy these zigzag relations. So the key insight is that once you have crossings, you can define a right cap to be a left cap, right? So here on top, this is a left cap. And then you attach a crossing to the bottom. And similarly, we can define a right cup in terms of a left cup with a crossing on top. Okay, so that's the key. So that gives us our definition of the right cap and cup. And then we just have to show that they satisfy this relation. Okay, so let's do that. So let's take the left-hand side of this equation. So we get this, and we want to show that it's equal to just a strand pointing straight up. Okay, so our first thing we have to do is we have to use the definition of these right caps and cups. So that was the twisted left caps and cups. So just use the definition of our right caps and cups here. Okay. Now, what I'm going to do is I'm going to take this strand here and this portion of this string here, and I'm going to pull this one across. And so they become this. Right, so that's what I did. I took these two and I just pulled them so they're double crossing, which I'm allowed to do in a symmetric monoidal category. Okay, so that's the first step. Now what I want to do is I want to look just at this piece of the picture where I've got this strand, and this strand. And you see this looks like half of the braid relation here. And so I pull it across and make it this strand, and this strand. You see, I use the braid relation just to pull that middle strand across the crossing. It's just the braid relation right in the middle there. Okay, now what I'm going to do is I'm going to take this cap and pull it through this strand, which I'm allowed to do because caps and cups, so I can just pull it out and it becomes this one. So I just pulled it across that strand. And now I do the same thing down here. I've got a strand and a cup that's crossing it. And I just pull that cup up through the strand and it becomes this one. And I've just pulled it through the strand, which I'm allowed to do in a symmetric monoidal category. And now what I've ended up with is this zigzag, but now it's got the left caps and cups, and that's part of what we had. So now that's equal to the identity strand. Right, so you see all we had to use was this definition of the right cap and cup and things that are true in any symmetric monoidal category. But of course, this only works in a symmetric monoidal category because we had to have crossings in these various relations. So we proved this left-hand side of 4.2. The proof of the right-hand side is almost identical. Basically, you just take this proof and just reflect our diagrams in the horizontal axis. Right? It's the same idea. Any questions there?
Right.
No, it also works in braided monoidal categories. You just have to be a little bit careful. You have to choose your crossing here. Oops. You have to choose this crossing to be an over and an under crossing. In your braid relation, you have to make sure that you're passing things over in the right way. But it's also true in a braided monoidal category that left duals are also right duals. Well, it's still true abstractly that V tensor W is isomorphic to W tensor V. It's just that the isomorphism is not the flip. So it's still true that it's both left and right dual. It's just that your isomorphism involves the R matrix now and is not actually just the flip. But what's nice about this is if you go back to our example of vector spaces, we showed that the dual vector space in the usual sense is dual in this categorical sense. We showed it one way, and then I said you could show that it's dual on the other side. Or I said it would follow from something later. This is the thing later. So vector spaces form a symmetric monoidal category. And so you could do this same argument if you wanted to show that the dual is also dual on the other side, once we've shown it's dual on one side. By the way, actually, let me back up. I just remembered one important thing to mention. I was on the previous slide, so let me just say it. You need to, when you want there to be duals for vector spaces, you need to deal with finite dimensional vector spaces. Because co-evaluation, if you remember, had this sum over a basis of V tensor, the dual basis. And that's an infinite sum if you have an infinite vector space. So in the categorical sense, the dual of the vector space is not its dual in this categorical sense. You're going to be a little bit careful there. That's why I keep saying, or I should keep saying, finite dimensional vector spaces. Okay, so what this proposition that we just proved says that if we're in a symmetric monoidal category, it's rigid if and only if all objects have left duals. We don't have to impose the condition that all objects also have right duals because that's automatic. Okay, and so remember that the duality, the cap and the cup, or the unit and the co-unit are not uniquely determined. But we'll always assume, we've just seen that we can always choose the right cap and cup to be related to the left cap and cup in this way. So we'll always make this choice. It makes our life easier and makes our pictures a little bit easier. And then an exercise is use this equation and attach appropriate crossings in appropriate places to show that you can also do the other way around. That if you have the right caps and cups, then the left ones are defined in terms of the right ones in this way. Okay. Okay, so now remember, we're assuming that C is a rigid symmetric monoidal category everywhere here. So for every object in C, we have an object X dual that's both left and right dual to it. Okay? Every object has a left and right dual. So a bit of notation now. So before when we give the definition, we just had up arrow and down arrow, but we may want to have different objects and their duals. And so just having one up arrow and one down arrow is not enough notation. So now we'll denote, if we have some object X, its identity map will be an upward oriented strand. And the identity map on the dual will be a downward oriented strand. Right? So by the way, that means that up labeled with X dual is the same thing as down labeled with X. Right? These are just two different ways of writing the exact same thing. So now we've got morphisms, we've got these left caps and cups, but we'll just label them with X because we may have many different pairs of objects with their duals. And then we have relations, but just things are labeled by X now. And we can choose our cups and caps. So just like this convention that I mentioned right here, where up arrow labeled X dual is the same as down arrow labeled X, a left cap where the up part is labeled X is the same as a right cap where the up part is labeled X dual, right? Because switching X to X dual basically reverses orientation, you should think, okay? And same thing for all our cups and caps. Any questions on that? Okay, so let's go back to compatibility between symmetry and duality in a monoidal category. Okay, so if we look back at this relation 4.7, it was exactly this relation, which is why I didn't bother rewriting 4.7. So remember, I left it as an exercise to prove that you can slide crossings over caps and cups. Okay, so this was that exercise that you can slide crossings over caps and cups. I just took a special case where you're sliding it over an up arrow labeled Y. So now if we take this relation and we attach a left cup to the bottom, rightmost bottom endpoint. So what that means technically is I'm going to tensor both sides with down arrow. And then I'm going to compose with identity, identity, left cap. So identity, identity, left cap. And I get exactly this equation. Okay. And now I'll use this zigzag, right? That if we had this zigzag, we can straighten it out. And I have a zigzag right here. So I'm going to straighten out that zigzag using this zigzag relation. And it gives exactly this equality. Right? So this left-hand side becomes exactly this left crossing. And this is exactly that right-hand side. So what this tells us, look, is that if we have the crossing between X and Y, then we can use the duality data just to rotate it, and that gives us the crossing between X dual and Y, right? So this will be important later when we wanted to build some universal category. We don't need to throw in all this and get crossings for the other objects, right? So that's the point of this, that there's this compatibility between the duality and the symmetry. Rotating a crossing gives you the natural crossing that you would think of if you think of just isotopy invariance. Say. Okay, so we proved this relation, but the proof of this relation is almost identical. Any questions here? Okay. So let's talk about one other thing we can do once we have all this extra structure of a rigid symmetric monoidal category. So again, our C will be a rigid symmetric monoidal k-linear category. And maybe again, I should also say strict. And we're going to make one more assumption. Our assumption is that when we look at endomorphisms of the unit object, this should just be some copy of our ground field. And what I mean precisely is we should just have scalar multiples of the identity endomorphism. So we should have this one-dimensional vector space, just multiples of the identity endomorphism, and that should give us all endomorphisms of the unit object. This is a pretty natural definition or assumption from the point of representation theory Because usually this unit object is the trivial representation, which is the one-dimensional representation, and its endomorphism algebra is just a copy of the field. Right? So in all our applications to representation theory, this assumption is satisfied. So it's not so strict an assumption for us. And we'll use this isomorphism to actually identify this endomorphism algebra with the ground field. So we'll identify an element of the field with the map of multiplying by that element. Okay, so let's suppose we have some object up arrow, and it's got a dual down arrow. And since we're in a symmetric monoidal category, I'm no longer saying left dual or right dual, because it's both left and right dual. So let's think about pictures we can try to form with this thing. So if we have some endomorphism of X, so that means some morphism whose domain and codomain are both the same object X. Then we can attach the left cap and the right cup and get this circle with this coupon label F. And where does this live? This is an endomorphism of the identity now. Right? You can see it in terms of pictures because there's nothing at the bottom or the top, or you just look at the domain and codomain of the cap and the cup. Right? So we can form this type of picture. It's an endomorphism of the identity, but remember we're identifying that endomorphism algebra with the ground field. So I'll just really say it lives in the ground field. Remember this identification, technically speaking, I'm viewing some element in this ground field as multiplication by that element. That was our identification. So we call this the trace of this endomorphism. And I'll justify in a second why we call it the trace, because of course the trace is a word you use already in linear algebra. But before that, let me give another exercise. One of the immediate things you may say is, well, I could have done another thing. I could have taken F and I could have attached cups and cups in the other direction. Right? Why didn't I do that? And in fact, it turns out that these are equal. And so that's an exercise. And so the hint is, remember, use this relation between our caps and cups in other directions. So you replace those one by the twisted one, and then use the fact that coupons slide through crossings, and you can move this coupon to the other side of that way. So it's a little one-line diagrammatic proof. Right? So that's why it didn't really matter what side we picked. So why do we call this trace? Well, let's look back to our favorite example, vector spaces, finite dimensional vector spaces over a field. But what I'm about to say also would apply to category of finite dimensional modules over a group or over a Lie algebra, the exact same proof of work. So let's look at this picture. So let me redraw this picture and break it into pieces. So we've got this, F, which for vector spaces is the one-dimensional vector space. And then we have this left cup. So their left cup goes to V dual tensor V. Okay, that's up to the first blue line. Then between the two blue lines, we have the identity on the dual tensor F. And then above the blue line, we've got the cap. Okay, so what do those maps do? That's how we've broken this sort of bubble into pieces. And this is uniquely determined by where it sends the unit element in the field. So let's look at just where the unit element is sent. Well, remember this definition of our right cup, because we defined, when we originally looked at vector spaces, we defined the left cup to be this co-evaluation map, which took 1 to the sum over a basis of V tensor V dual. That was our co-evaluation. But here we have the right cup, but that's just the left cup followed by this crossing. So we just take this map and then we just swap the two factors, because the crossing for vector space is just the tensor flip. So our map takes 1 to this sum, where we just have the delta V on the left and the V on the right. That follows from our definition of the right cup. And now we apply F to the second factor. So we apply F to all these V's. And now we apply Now we're up here and we need this left cap. Again, that's evaluation, which we defined before, right? So it's exactly evaluation. So we just take this dual element and we evaluate on F of B, and then we get this sum. But if you think about it, that's exactly the usual trace of a linear operator, right? You take a basis, you apply F to all your basis elements, and then you take the components in those same basis elements and you add them all up. That's exactly the trace. So if you pick a basis and you write your F as a matrix, it's the sum of the diagonal entries, right? It's the usual trace. So under our isomorphism of endomorphisms of the unit with the ground field, this bubble is exactly the trace. You know, technically it's the endomorphism of the unit that's multiplication by the trace, right? But under our identification, it corresponds to the trace. Any questions on that? Okay. What's the one special example of the trace? Well, if you take the trace of the identity map, if you're, say, in category vector spaces or sort of the algebras, the trace of the identity map is just the dimension of the vector space, right? So this gives us a way to, in the abstract setting of symmetric monoidal categories, rigid symmetric monoidal categories, to define the dimension of an object. So the categorical dimension of an object, up arrow, is just this bubble. It's just a special case of the trace where we've got no F on the right-hand side because we just take the identity map. So it's just that bubble. And that bubble is an element in the ground field. I mean, technically speaking, this is an endomorphism in our category of the unit object, but we identified that with the ground field. So we think of it as a scalar. But note it can be anything in the field. So of course you're used to in representation theory, dimensions are positive integers. But in theory, you can have a category that doesn't have any connection to vector spaces where you can have a dimension that's anything in the field. You can have some irrational dimension. You see this, people may have seen things like Deline's interpolating categories. That's sort of what's going on here. You can have an abstract monoidal category where your object can have a dimension that's not a positive integer. But we've seen from our discussion up here that if you are dealing with something concrete like vector spaces, this does correspond to the usual dimension, right? So we're justified in calling it dimension. And a special case of the exercise that I wrote up here, this exercise that the bubbles in the two directions, the two types of trace you could form are equal. A special case of that where F is the identity means that both the left and right bubble are equal. So this says that the categorical dimension of an object is equal to the categorical dimension of the dual object, right? Which coincides with what we think of for vector spaces. Vector space and its dual have the same dimension. Only if we deal with finite dimensional vector spaces. Remember, this all only works for finite dimensional vector spaces. Okay, any questions? Okay, so in the last 5 minutes, the next thing I want to do, which we won't get all the way through, but maybe I'll just start. We now want to do this idea of forming a universal category, but now we want our category to be the free, rigid, symmetric monoidal category on a single object. So what we've seen so far is the free symmetric monoidal category on an object. In some sense, the free rigid monoidal category on a single object. It's a little bit different. We had the free monoidal category in an object that had a two-sided dual. That was the oriented temporal lead category. And now we want to define a universal category that has both of these. So it's symmetric monoidal and it's rigid. Okay, so let's just start this and then we'll finish it tomorrow. This category, that's the OBC in the title here, will end up being the oriented Brauer category. But instead of just giving you the definition, I really want to motivate the definition. We're going to build it up from scratch, see exactly what we need to throw in to come to this definition, and then I'll restate the definition at the end. So let's just start this process. So we'll pick some generating object up arrow. Okay, so we need two things. We need to add in a dual because we want our category to be rigid, but we also need to add in some crossings. Because we want our category to be symmetric monoidal. And you can sort of choose which one you do first, and it leads to two different definitions, equivalent definitions of the oriented Brauer category. So we're going to pick to do the duality first. Well, half of the duality first. So we'll first add in another object, left arrow, that is left dual to up arrow. So we have the left cap and cup and the left zigzag relations. Eventually, we want this to also be right dual, but we've seen that if we make our category symmetric monoidal, it'll come for free that this thing is also right dual. So instead of adding in now right caps and cups, satisfying the right zigzag relations, we're going to now shift and make it symmetric monoidal, and that part will come for free. But this is where your two approaches diverge, and you could get two equivalent definitions of the oriented Brauer category. You could add in the right caps and cups now, and that'll change a little bit how you approach the symmetry. Okay, so we're going to focus on making our category symmetric monoidal.
Obviously, the result is independent of the choice.
That's right. You get two different presentations of the same category, and you can show that they're isomorphic, these two categories. But they'll have different presentations, different sets of generators and relations. Okay, so we want to make it symmetric monoidal. That's our goal now. So we got to add in a crossing. Okay, let's add in a crossing just for the up arrows. And then we need to start adding in some relations. This should be a symmetric monoidal category. So we need to have this relation. So we'll put that in as a relation. And now you might think, well, we also have this down arrow. I need a down crossing. And I need the crossings for up and left, or up and down together. So I need all sorts of crossings. But before I start throwing those all in as generators, this is where we should pause and slow down and think, well, maybe from the ones I already have, I can start getting some of these other crossings. And in fact, we can. We saw this trick. So we can take our up crossing and we can attach left caps and cups and rotate it. So we'll define our left crossing in this way. So we don't need to throw that in as an extra generator. We have enough to get a left crossing. And we need a down crossing, but we don't have to throw that in as a generator, because we can take this left one now that we've defined and rotate one more time. Or you could define it directly. It's the up crossing where we've rotated both of them, right? So that's now a down crossing. And now an exercise, you can take this relation up here, you can attach caps and cups and rotate it around and get this relation for free. So we don't have to put that in as a relation. But we're missing one crossing, which is this right crossing, right? Because we also need the symmetry data for up-down, right? Which is the right crossing. And you see, we can't do the same trick by rotating the up crossing because we don't have right caps and cups. If we took the other approach to this oriented Brauer category, where we first introduced right caps and cups, we could do this. This is where these approaches start becoming different. But we don't have right caps and cups, so we can't do this trick for the right crossing. But then you might think, well, wait a minute, we defined a right crossing in terms, or we don't have the right caps and cups. And you might think, wait, we defined right caps and cups in terms of the left ones. So why can't we do that same trick? But then you realize that when we did this, these have a right crossing in them. So there's a catch-22 here, right? We have to throw in something. Either we have to put in the right, and then we can define the right crossing, or we have to put in the right crossing, and then we can use that to define the right caps and cups. And that's where the two approaches diverge. So what we're going to do in our approach, and this is where I'll stop, is we're going to introduce this right crossing. And then we'll impose some more relations, and we'll see that this is all of the generating morphisms we need, and we're just going to need a couple more relations, and that will be it, and that'll be the oriented Brauer category. But I'll continue that next time.